So this is going to be section 1.7 of my pre-algebra series, and here we're going to talk about multiplying and dividing terms. So again, just some more of the algebraic rules that tell us how to simplify expressions using multiplication and division. And that's what it says we're basically going to do here. Just find the product and quotient of two algebraic terms using properties of exponents. So we'll talk about the formulas and try to come up with some notation here, and then we'll just do a bunch of examples. Okay, so suppose we've got this notation here, and this is what we call exponential notation. So I've got this number at the bottom, and again, that's what's known as our base. So we have this base of 3, and then we have this exponent, that's the number upstairs. We have this exponent of 5, and what is that notation shorthand for? Well, this number at the top, this exponent, that tells us how many times we have the base multiplied by itself. At least we can think about it in that respect if our exponent is a positive whole number. We can at least think about it that way. So 3 to the 5th, that says I have the base of 3, but it's going to be multiplied by itself 5 times. So 3 times 3 times 3 times 3 times 3, and whatever that equals to, that's going to be our solution. That's what 3 to the 5th is equal to. Okay, all I really care about is that when we write this exponent, we're really talking about repeated multiplication. So if I had x to the 4th, what would that mean? Well, in that case, it just simply means we have x times x times x times x. We've got 4 x's being multiplied together. So let's think for example, if we have x times y to the 3rd all being squared, well, that means I have x times y to the 3rd. It means I have 2 of those. Let me make that one look a little better. So I've got x times y to the 3rd, and then x times y to the 3rd, right? I've got that xy to the 3rd, but I've got 2 of them multiplied. And in this case, I could even simplify. So this is all multiplication, so I could multiply my x times my x, and I could multiply my y to the 3rd by my y to the 3rd and simplify. And we'll talk about that as we move forward, how we could simplify that a little bit further. So let's think about what happened. You know, if we have these like bases, notice I've got x raised to the power of 5 and another base of x raised to the power of 3. If I take x to the 5th and multiply it by x to the 3rd, what should that simplify to? Is there a nice little algebraic formula? Well, x to the 5th, that just means we have 5 x's being multiplied by each other. So there's 5 x's. And then it says we have 3 x's being multiplied by each other. So x times x times x. Well, if you were to simply count all of these x's up that are being multiplied together, we have 8 x's all being multiplied together. So that simply tells me that x to the 5th times x to the 3rd, that's going to equal x to the 8th. And that gives us our nice little rule as follows, this property of exponents. It says for any positive integers m and n, so any positive integers m and n, and any real number a, it says a raised to the power of m times a raised to the power of m is a raised to the power of m plus n. So what it says is when we multiply like bases, right, here's a like, these two bases are alike, I've got the same base. So we're multiplying like bases, right, we're multiplying those like bases. It says take those exponents and add them together. And again, that's all we did here, right? We took these exponents, 5 plus 3, and we got 8. Again, recognizing that we're multiplying like bases. Certainly have to have like bases. So let's do a couple examples here, nothing too crazy. So x to the 5th times x to the 10th, well, those are like bases. I would add those exponents. So I would have x raised to the power of 5 plus 10, or x raised to the power of 15. X times x squared, well, that's really x to the 1st times x squared. So that's x raised to the power of 1 plus 2. I'm just adding those exponents. That's x to the 3rd. And of course, people typically will not, once you've done some of these, you're not going to write these middle steps. I'm just emphasizing the rules, at least in those first two examples. They are correct, but people will just skip those. So let's skip, for example. I've got 4 to the 5th times 4 to the 6th. Be careful sometimes when people see bases. So these are like bases, but when they see that they're numbers, sometimes they'll multiply them together and do all kinds of weird things. We're doing the same thing, right? We leave the base alone. We recognize they're like bases, so we leave it alone. So I'm going to leave that base of 4 alone. And again, all I do is add the exponents. So 4 to the 5th times 4 to the 6th, that's going to be 4 to the 11th. And of course, since we're dealing with numbers, you could multiply out 4 to the 5th and 4 to the 6th and multiply them together and get whatever 4 to the 11th is. But again, we're just trying to emphasize those properties of exponents. Well, my last example, the only thing that's really new is instead of having 2 like bases, now I've got 3 like bases. So z to the 4th times z to the 10th times z to the 3rd. Again, all I'm going to do is recognize that those are all like bases of z. And since it's multiplication, we simply add those together. So 4 plus 10, that's 14, plus 3, that's 17. We'll get z raised to the power of 17 after we simplify. All right, let's do a few more. So now the same thing. Okay, so I've got 2x to the 4th times 10x to the 5th. This is all multiplication. Well, let's just multiply the numbers. 2 times 10. 2 times 10 is 20. And then I recognize my like bases, so x to the 4th and x to the 5th. Well, I've got that like base of x, my like base of x. And then I'm going to add those exponents. 4 plus 5 is going to give me 9. So 20x to the 9th will be my solution. Okay, let's do another one. Let's see. So we can take a couple steps here. So I'm going to take the 4 and multiply that by the negative 1/2 and multiply that by the negative 5. This is really what we're kind of doing. This is all multiplication. So we can multiply in any order we want. And then I would take my y to the 3rd times my y to the 6th. I would also have to multiply those together. So y to the 3rd times y to the 1st times y to the 6th. Well, let's see. The first thing I think is I've got a positive. My first number is positive times a negative. That's going to give me a negative. But then a negative times another negative is going to give me a positive. So I know at the end of the day this is going to be a positive number, but I'm not going to write the positive. So now forgetting about the signs, I have 4 times 1/2. 4 times 1/2, well, that's 4 over 1 times 1 over 2. We could write that as 4 over 2 or 2. So 4 times 1/2, that's 4 divided by 2 or simply 2. And then I would have to multiply that. So I've got, and I'm forgetting about the signs, remember, because I've already said that this is going to be a positive number. So we can forget about the signs for now. So 4 times 1/2, we said that's 2. But then I would have to multiply that by 5. So 2 times 5 is going to be 10. So I know that I'm going to get, if we go back, so 4 times negative 1/2, that's going to be negative 2. And then negative 2 times negative 5 is going to be positive 10. And last but not least, okay, we've got all these like bases, y, y, y. So we're going to get a y. And then we just add the exponents. So again, my middle one there, that's going to be a y to the 1st. So 3 plus 1, that's 4. 4 plus 6 is going to be 10. So we actually get 10y to the 10th if we simplify that down. And of course, I showed a lot of extra steps. Once you've done a few of these, you'll simplify these down rather quickly. Okay, now for division. So if we had like bases that were multiplied, right, if we multiplied like bases, we added the exponents. Instead of multiplication, we've got division. What might you think happens with the exponents? And well, I think we can come up with a good guess here. Suppose we have x to the 6th. Well, that's 6 x's being multiplied together. So there's my 6 x's. And then x squared, that means we have 2 x's being multiplied. But since this is all multiplication in the numerator and the denominator, we can cancel out some common factors. So x times x would cancel out, and then I could cancel out another x and another x. And I can still imagine that I'm multiplying the denominator by 1. So in the numerator, what am I left with? Well, I've got 4 x's being multiplied together. That's x to the 4th over 1, or simply x to the 4th. So it says the moral of the story is that x to the 6th divided by x squared, that equals x to the 4th. Well, how do we get a 4 from those exponents of 6 and 2? Well, it looks like if we subtract, if we take 6 minus 2, right, this exponent minus this exponent, we will get x to the 4th. And in fact, that is going to be our rule, is that we'll simplify. Okay, so let's put this down here. So basically, x to the a over x to the b, that's going to equal x raised to the power of a minus b. And we'll use the same restrictions that we had previously as well. Okay, so we don't want x, for example, we don't want x to be 0. So with those conditions that seem reasonable. Okay, so be careful because again, like y to the 12th divided by y to the 3rd. I see division in this problem, and people sort of have that in their brain, and they want to do division. So be careful here, because again, I recognize I'm dividing like bases. I have to subtract the exponents. 12 minus 3 would give me y to the 9th power. That would be the correct solution. A very incorrect thing to do, and be careful, it's a very common mistake to make. So be careful about this. Y to the 12th over y to the 3rd. A lot of people will see division, right? They say, oh, division. And then they'll divide this, 12 divided by 3. They'll say, oh, 12 divided by 3, that's 12 divided by 3 is 4, and they'll get y to the 4th. But of course, this is not correct. And the reason it's not correct is just simply, again, by this argument, right? You're just canceling out you're canceling out 3 of the y's in the denominator with 3 of the y's in the numerator. And that's going to leave you with 9 y's left over in the numerator. So if you ever get one of these questions and you're like, what do I do? Just ask yourself, what does this exponential notation mean? And then you'll remember, say, oh, I should be subtracting those exponents, not doing this division. That doesn't make sense. Okay, so let's do another one here. A to the 5th times b to the 4th over a squared times b. So I'm going to sort of separate these in just as 2 separate little questions. So a to the 5th over a squared, if I take that exponent of a raised to the power of 5 minus 2, and then I would have b raised to the power of 4 minus 1. And if we simplify, that's just going to leave me a to the 3rd power and also a b to the 3rd power. Be careful, my a's tend to look like 9s sometimes. That is supposed to be an a. So let's do one more example. Now, you may be asking yourself a couple questions here, and maybe not, but let me pose them to you. Notice that the exponent in the numerator is always bigger than the exponent in the denominator. What does it mean to get a negative exponent? What does it mean to get a fractional exponent? What does it mean to get an exponent of 0? So these are things that we'll discuss in the future, moving forward. Okay, so one last example. We've got 10 times x to the 4th times y to the 7th times z to the 3rd, all over 5xy z squared. So I'm going to write out most of the steps here just one last time. It's really just a bunch of division problems using this property of subtracting exponents. Well, I see a 10 divided by a 5. A 10 divided by 5 is just 2. And if I do x to the 4th over x to the 1st, well, now I'm going to subtract those exponents. So I'm going to have an exponent of 4 minus 1. So I would have an exponent of 4 minus 1, or x to the 3rd. Next, I see this like base. I see y to the 7th over y to the 1st. So I would subtract those exponents, 7 minus 1. That's going to leave me with a y to the 6th power. And last but not least, if I look at my z's, I've got z to the 3rd over z squared. That would be z to the power of 3 minus 2, or z to the 1st. And when it's just to the 1st power, we don't even write it. So that would simplify to 2x to the 3rd, y to the 6th, z to the 1st. Okay, so if our base is not equal to 0, what is some non-zero number raised to 0? What does that equal to? So for example, what does 7 to the 0 equal? What is 4 to the 0 equal? What is pi raised to the 0? What does that equal? Well, let's think about it. So suppose I just made this at random, x to the 4th over x to the 4th. Well, if x is not 0, you can think about it this way. Pick your favorite number for x. You're going to get the same number after we raise it to the 4th power. We'll get the same number in the numerator and the denominator after doing the arithmetic, is what I'm trying to say. Well, if you take any number and divide it by itself when it's not 0, you just get 1. So x to the 4th over x to the 4th is going to be equal to 1. It's like having, 10 over 10, right? 10 over 10 is 1. Get the same thing on top, same thing on the bottom. But if we use our properties of exponents, well, I would get the power of 4 minus 4. That would be my exponent. And that's going to be x to the power of 0. So what we do is we define x to the 0 to be equal to 1, so long as x is not equal to 0. So anything raised to the 0 power, again, assuming it's not 0, is always going to equal 1. So keep this in mind. Another very common mistake, people will say, they'll see this exponent of 0 and say, oh, I guess it just equals 0. But that is not correct. And it makes sense in conjunction with this property of exponents. That is what we should define x to the 0 to be equal to make sense. Okay, so let's look at a couple of these. I've got a couple of these. I want to know if both of these simplifications are correct. And I'll let you think about this. So in the first one, I've got x squared times y divided by x squared. And it looks like I've just canceled out an x squared and I'm left with y. So I'll ask you, is this correct? And then in my next one, I have x squared minus y over x squared. And it looks like I'm saying, well, x squared over x squared, that's equal to 1. And then I still have my minus y left over, right? My minus y, there's my minus y. So if I cancel those and get the 1, are both of these correct? And I'll let you think about which of those is correct. And maybe they're both correct, maybe neither one. And when you answer that question, think about how you would pick out, what would tell you when you can do this cancellation of these common factors. What has to happen, and when should you be careful to not do it? Okay, so let's just look at a few more examples. I think I've got, it looks like we've got quite a few here, so let's run through these real quick. And as always, if you feel confident, feel free to pause and jot these down and try to practice them. And then you can compare what you get with what I get. So a few different ones. And I will step through these a little bit faster. Okay, so b to the 9th times b, which is b to the 1st. Well, we just add those exponents. That's going to be b to the 10th. Now, again, I see all of this multiplication going on in my next example. I see these bases of a, and I see these bases of b. Well, if I take the bases of a, I'll just add the exponents. So I'm going to add a 3, a 2, and a 5. So 3 plus 2 is 5 plus another 5. That's going to give me a to the 10th. And then I'm going to do the same thing with b's. I've got a b to the 1st, a b to the 4th, a b to the 6th. 1 plus 4 is 5, plus 6 is 11. So I'm going to get a to the 10th times b to the 11th. Okay, again in part C, all multiplication. I've got a positive 5 times a negative 5. I would say, okay, that is negative 25. Now I look for like bases. I've got m to the 3rd, m to the 4th being multiplied. That would be m to the 7th. And then n squared times n to the 5th. Like bases, add the exponents. Again, be careful if you're flying through these on a test. It would be really easy to make a mistake and accidentally, mess up the exponents. Okay, so negative 25, m to the 7th, n to the 7th looks like the solution for part C. Part D, okay, we've got, some more factors. So 2 times 2 times 2, 2 times 2 is 4, times another 2 is 8. I see all these like bases of x. Let's just add the exponents. 5 plus 4 is 9, plus 3 is going to be 12. So 8 times x to the 12th. can do the same thing on our next one. I see a 2 and a 2. That's a 4. We've got that like base of, oh, we don't. I almost made a mistake. So we've got 2 times 2, which is 4. I just assumed. Okay, so notice we don't have like bases now. We've got x squared and we've got y squared. Those bases are not the same. We can't combine them. So I could multiply the 2 and the 2. That's legal. But then we've just got our x squared, y squared along for the ride, which is fine. Okay, so our next example, 10 divided by 5, that is 2. M to the 6th divided by m to the 3rd. Again, be careful. We are dividing like bases. Subtract the exponents. 6 minus 3 is going to be 3. Let's keep going. 48 divided by 6. What is 48 divided by 6? Well, I think 48 divided by 6 is 8. Then I've got p to the 4th over p squared. So p to the 4 minus 2 is going to be to the power of 2. And then I've got q to the exponent of 7 minus 3. 7 minus 3 is going to be 4. Okay, now I've got x to the 3rd all squared. We didn't talk about this rule, but think about this. So, I'll point out one other thing as well. So we've got x to the 3rd squared. What does that mean? Well, that means we've got x to the 3rd times x to the 3rd, right? We've got x to the 3rd multiplied by itself twice. But now that's one of the examples we've been talking about. We've got x to the 3rd times x to the 3rd. Add the exponents, we would get x to the 6th. So kind of compare that. Think about, because this is another common mistake. Think about x to the 3rd squared. Think about what we got there, right? We just did that. We got x to the 6th. Compare that to x to the 3rd times x squared, right? Clearly those are different. We've got this extra x floating around on the left side. And in this case, we would get x to the 5th. So do be careful about these two very different expressions, equations, examples, because that, again, is a very commonplace. People will make a very fundamental algebra mistake. So with that in mind, let's even use that, right? It looks like, in this case, it looks like we multiply the exponents. So if I have x to the power of a raised to the power of b, again, under appropriate values of x and a and b, what we'll do is we'll actually multiply those two numbers together, just like this example showed. So I've got x to the 5th all to the 3rd. Well, again, I could write that as x to the 5th times x to the 5th times x to the 5th. Or I could have just multiplied those together, which again makes sense because we would have 5 plus 5 plus 5. Whether I multiply or whether I add those exponents together, in either case, I'm going to get the correct solution of x to the 15th. All right, let's do one more. Negative x y squared, all of that being raised to the 3rd power. Well, that's negative x y squared. It says we've got that multiplied by itself 3 times. Okay, so at least this is how I think. I think a negative times a negative is a positive times a negative. That's going to be a negative. So I know I've got a negative. So at this point, I'm forgetting about the signs. I don't care about the signs anymore. I've already accounted for the sign in my solution. Okay, I see like bases. I've got x to the 1st, x to the 1st, x to the 1st. If I add those exponents, I would have x to the 1 plus 1 plus 1, or x to the 3rd. And last but not least, I would have y to the 2nd times y to the 2nd times y to the 2nd. If I multiply those like bases, I would have y raised to the power of 2 plus 2 plus 2, or lastly, we would get y to the power of 6. Okay, so some very fundamental properties of exponents. You will use these day in and day out on your math journeys for sure. This is something you'll see all the time when you're simplifying equations, expressions, whatnot. So definitely be careful. And again, if you ever forget, should I be subtracting, dividing, multiplying, dividing, just stop and ask yourself, make a quick little example and think, what does this notation mean? And make a little example, and I think you can quickly derive the correct formulas that you should be using.